Today I will tell you about my work on the structure of dark matter on small scales, in particular how to look for it. So how do you look for very small dark matter substructures of the Milky Way, so small that they would not obviously show up in this image. So I'm not going to show you a pie chart of dark matter, nor a picture of Fritz Zwicky or Vera Rubin, because in fact, the first time that we inferred the presence of a massive body from its gravitational influence occurred much earlier, in 1846, when Urbain Le Verrier predicted the position of a new planet that we later found out to be Neptune, and which was, of course, not so dark. And I'll get back to planets later in the talk. But more seriously, the body of evidence for the existence of dark matter is vast, and in particular, one body of evidence with very robust predictions is the study of large-scale structures in our universe. So we know dark matter is a cold, collisionless fluid on very large scales that clusters from very small fractional density perturbations to the nonlinear structures today. We know the initial density fluctuations were fractionally very small by observations of the cosmic microwave background, and yet another robust probe of the presence of dark matter. Today, we live in the Milky Way, which is a very nonlinear structure that formed the evolution of those tiny density fluctuations. And you see here satellites, other nonlinear structures, such as the Magellanic Clouds here in this picture. And there's many more. So here I'm showing the dwarf galaxies and their motion, as well as globular clusters, in a number density map produced by the Gaia collaboration, so a number density map of point sources. And in fact, this image is not really an image in the traditional sense, that it's not a CCD exposure. It's in fact a map of point sources detected by the Gaia collaboration, colored by their approximate color and multiplied by their flux. So it's a bit distorted from what you normally see, so Andromeda is less bright because they see fewer point sources there. Okay, so today I will mostly talk about new observational probes to detect substructures of the Milky Way that are much, much smaller than the Magellanic Clouds, so small that they would not contain any baryons or even stars. No stars and not even baryons. So this is a cartoon overlay of what this could look like. So very small clumps in the Milky Way that do not emit light because they do not contain any stars. So before I get to that, let me tell you a little bit of what could source these small halos. So in particular, primordial fluctuations and dark matter microphysics. We've measured the cosmic microwave background exceptionally well on the very largest scales in our universe. So from the largest scale in our universe down to about a megaparsec or so, we measured the power spectrum of initial curvature fluctuations quite well, and it's consistent with being nearly scale invariant with a slight tilt, and also on smaller scales around comoving wave numbers of an inverse megaparsec, we've measured the power spectrum also reasonably well. I just want to show you here that there's a lot of room for change at smaller scales. So here we do not have good probes, but by observing tiny substructures of the Milky Way using the methods that I'll describe later in the talk, I think you can have discovery reach for primordial perturbations in this regime. So in particular, enhancements of the power spectrum current probes and with future probes, we think we can detect even standard primordial curvature fluctuation spectra. Instead of modifying the initial conditions, so the primordial fluctuations, it's possible that dark matter behaves differently on small scales as well. So one could suppress small scale structures or enhance them. Historically, for observational reasons, there's been a lot of focus on suppression of small scale structure. So in particular, dark matter could be warm, so you could have a large pressure from its velocity that suppresses structure on small scales. Likewise, dark matter could be an ultralight scalar field with a de Broglie wavelength that's on galactic scales that causes a gradient pressure, which in turn again suppresses structure on small scales. Or by David and collaborators, if you have self-interacting dark matter, that could erase structures in small dwarf galaxies, for example. On the other hand, and this has received less focus, you could also enhance small-scale structures. So if you have any dissipative interactions of dark matter that can cool a halo and make it more compact. Likewise, instead of being sourced by primordial fluctuations, dark matter can do lots of stuff on small scale. So for example, there could be phase transitions in a dark matter sector that cause large density perturbations at small scales. I've studied a model of axion self-interactions. So it's ultralight scalar fields, but where you now include attractive self-interactions that are generically there. So if you study how small fractional density perturbations, delta sub k, do on subhorizon scales, if you have cold dark matter, the sound speed is essentially 0, and structures grow, for example, linearly during matter domination. However, for light scalar fields, there's a positive sound speed contribution, or positive pressure, that erases structure, and why we usually call them fuzzy dark matter. However, there's a negative contribution as well from attractive self-interactions that can cause a huge boost in structure on small scales. So in this graph, I show you the scale density of a typical subhalo as a function of subhalo scale mass. So the black line is what you would expect in a cold dark matter scenario with the scale invariant power spectrum. But however, if the dark matter is made up of a light axion field with self-interactions, it would have the same halo mass function at high masses, but there could be a large increase in the typical density of a halo, in this case at 10 to the 4 solar masses, so enhanced by some boost factor B here at one particular scale. This can happen at any scale, so these boost factors can be exponentially large, and the scale at which this happens is set by the axion mass. It scales like the axion mass to the -3/2 power. So you could enhance structures at 1 billion solar masses down to 1,000 solar masses, etc. And I won't go into more detail about this in my talk, but feel free to talk. Yes?
Sorry, it's set just by the axion mass, not by the self-interactions.
Basically, yeah. There's small dependence, but not very much. Yeah. And in this scale here, this K star is usually the scale where you have suppression. So for example, if you look at the red curves here, if the mass is 10 to the -15 eV and it was a free scalar field, then there would just be suppression at a certain scale. But instead, if now you have interaction, instead of a suppression at the scale, you first have an enhancement and then a suppression. And it's mostly set by the mass and only logarithmically sensitive to the self-interaction. The size of the self-interaction sets the enhancement. Okay, so there's multiple ways in which we could change dark matter on small scales. So it could either be from primordial fluctuations or from dark matter interactions or dark matter microphysics. So how do you look for it now? So how do you probe this very small scale structure? It's quite difficult, right? Because there's no stars in these structures. So you have to use the gravitational coupling of these small objects. You can try to look for distortion in strongly lensed systems, and there's a lot of work in this area, a fraction of which I'm showing here. So for example, you can look for multiply imaged quasars and compare the flux ratios between the quasars, and substructure in the strong lens could affect these flux ratios. You can also look for extended strong lens emissions and perturbations thereof, which could reveal the presence of subhalos, which is a promising technique in now that ALMA's come online. And you can also look for, and this is on much smaller scales, irregularities in photometric microlensing light curves of stars that traverse a caustic. Alternatively, you can also look in our own Milky Way by the gravitational kicks it gives to dynamically cooled systems. So there's been some work by Daniel and other people here in the New York City area about this, where you could have a gravitational impact kick away, give a velocity kick to stars, which causes a gap, and then a secondary stream or a spur. And in fact, there's a tentative detection of such a interaction here that seems to indicate a roughly million solar mass clump that intriguingly is slightly denser than what you would have expected in a cold dark matter scenario, but still consistent with it. You can also look for, not just for strong lensing or weak lensing of light, you could look for lensing of gravitational waves as well. And this is work by Liang Dai and collaborators that is very exciting in the current advanced LIGO area. Historically, these probes have been very sensitive, looking for very compact dark objects, such as primordial black holes. However, they're not so sensitive for more extended subhalos that collapsed in standard cosmological scenarios, because they're too fluffy. So these are amazing probes that some of which are more sensitive than the method that I'll be talking about today. But I think we have a complementary method that will increase in sensitivity in time by a very large amount. And this was a proposal that I wrote with Neil Weiner and a graduate student at NYU, Anna Maria Taki, who's now a postdoc at Oregon, that we called Halometry from Astrometry. So we think you can leverage the giant leap in precision in statistics in current astrometric surveys, basically the discipline that looks for the location and motion of luminous sources, to do the same thing for dark structures, so halometry. So we think we can have direct measurements of the location and the motion of completely dark objects in the Milky Way halo. And we propose doing this with time domain astrometric weak lensing, so where we look for time-dependent effects in the angular deflection of weakly lensed stars. So I will tell you about the basic effects of our that we suggested in our proposal, and then towards the end of my talk, I will present an analysis with the same collaborators and a fantastic graduate student at NYU that's doing a local analysis of this effect for single subhalos, as well as an analysis that looks for a global population of these structures in the Milky Way. The first one is coming out on the archive tonight, and the second one should appear this month as well. So this is the outline of my talk. I will present the basic physical effect first, and what the observable signatures are. I will then talk about the local analysis that is appearing on the archive tonight. Tell you a little bit about the global analysis that looks for global populations of subhalos. And then I'll conclude with a future outlook with sensitivity summaries, with future data sets and future surveys, and some of the other things, transient signatures that you can do with those that are currently not yet possible. Okay, so what's the basic physical effect? So you've likely all seen this. So suppose we have a source I here that we're observing, but whose light path is slightly deflected by a lens L with impact parameter B. The lensing deflection is of order 4 times G times M over the impact parameter. And for a cold dark matter subhalo, let's say of 1 million solar masses, this one is expected to not contain any baryons whatsoever. And in a cold dark matter scenario would be about 100 parsec in size. So if the impact parameter is of order its size, then the angular deflection that we see would be 400 microarc second, which is bigger than the typical light centroid uncertainty in, for example, the Gaia survey. So you may ask, why haven't we seen this yet? If it's bigger than even the light centroid uncertainty for a single star. And the basic problem is that the true positions of the stars are unknown. So if they were, let's say if they were in an exact rectangular grid, which they're not, and then you put a lens there, we claim that, of course, you can see this deflection if it's bigger than your uncertainties. However, in the real world, stellar fields look something like this. And if you plop a lens down there, if you could turn on and off the lensing, you could see it. But of course, the density decrease behind the lens is smaller than the typical density variations, even just from Poisson noise. The second problem is that for extended lenses, such as cold dark matter subhalos, the lensing effect, which is proportional to the enclosed mass over the impact parameter, goes to 0 for large lens radius. So the solution to the first problem is to not look at the static effect, but instead at a time domain effect. So what happens if the halo moves, or we, the observer, move? And there's no solution to the second problem, but we can recuperate some of the suppression by the big lens size by using the fact that many stars are eclipsed by a big lens. So we can use the fact that the deflection is correlated for many stars behind the lens, or around the lens. So let me tell you about the observable signatures. So in this case, for very compact objects. So here I'm plotting just a stellar density field with a compact object moving through it. So you can look for these transient motions that we call blips. So they're non-repeating transients that are very telltale. So it's not a circular motion and it's non-repeating. It can actually occur for if the lens is traversing a big enough path on the sky. It can actually occur for many stars. So you can have a very robust signature where you can even retrace with high accuracy the path of the lens, and also reject systematics of mismeasuring one particular star. Or you can look, suppose these stars were extragalactic and not supposed to move, you could, with good measurements, you could potentially infer the presence of a lens by an anomalously high velocity or acceleration of a star. But most of my talk, I will talk about these extended subhalos. And so if an extended halo is moving, so of course it distorts the position of the stars, but because it's moving, it is also distorting the proper motion of the stars. So here, in this mini cartoon simulation, the stars are actually, the true position of the star is fixed, and the motion is just induced by the motion of the lens. And as you'll notice, outside of the lens density profile, you get a dipole velocity pattern outside the lens, and then the inside of the lens, the velocity pattern inside the lens is determined by the density profile of the lens. So we suggested doing a matched filter analysis of this local dipole velocity pattern, and that's one of the analyses that I'll talk about later today. Likewise, you can also look at the two-point function, for example, in the proper motions or accelerations of stars, using the fact that nearby star pairs typically get common lensing corrections. Okay, so I showed you numerical estimates for the size of the static effect. Of course, the lens is moving at some velocity VL. We are moving, and the star is likewise moving. So this will induce these time domain effects. You can look for these monoblips if the path that the lens travels over the duration of your survey is larger than the impact parameter with the star. And for what I'll be talking about most today is this angular velocity shift. It's much, so basically it's the lensing deflection, the first time derivative of the lensing deflection, which is the same formula as before, but now multiplied by a factor of this effective lensing velocity VIL divided by the impact parameter. And so if you plug in the same numbers as before, a million solar mass halo at 100 parsec impact parameter, you get 10 to the minus 3 microarc seconds per year. So this is still much below the current sensitivity of astrometric surveys for a single star. But of course, if the substructure is enhanced, there could be smaller impact parameters and smaller halo sizes. And likewise, accelerations, there's another factor of V over B suppression from the extra time derivative. But this also means that very small masses and very compact objects are potentially probable using accelerations.
Can I ask something?
Yeah.
When you say template, do you mean
Yes.
a template for an individual star or a template for a collection of stars?
You could do a collection of stars, but we will look for evidence of a single lens across the sky. Yeah.
So you take into account the proper motions of all the stars in the dimension.
Yes, but typically what dominates is the observer and lens velocity. Yes. Yeah, and the observable is on the proper motion of the stars. Yes.
I guess what I'm saying is if you can look for a pattern, not just for a pattern in the velocity change of a single star, but for a pattern which is...
Yes, in a collective pattern of multiple stars.
Is
Yes.
this what you're doing?
Yes, that's what I will be doing. Yeah, thank you. But yeah, so let me also tell you about the statistics. So instead, we look for time domain effects. Another thing that helps us is the large statistics in the Gaia survey. So if you look at the number of lens sources behind 100 parsec radius lens, that's 10 kiloparsec away from us in line of sight, with a typical stellar number density, so 10 to the 8th per steradian for the Gaia survey, you see that the number of stars eclipsed by the lens is about 10,000. So, and indeed, the pattern is correlated for all of those 10,000 stars, which helps us beat down the noise. And likewise, if you want to look for these blips, you require that the impact parameter is much smaller than the path traveled by the lens. And indeed, because you have many stars in the Gaia survey, you occasionally find very small impact parameters. So these blip motions do occur. For example, for lens masses of order of solar mass that only make up a tiny fraction of the dark matter density. Okay, I'll get to the analysis in a second, but let me give you a flash review of Gaia astrometry. So Gaia measures the position of stars as a function of time, typically in one direction much better than the other. But it does so many times, of order 100 per star. And then it fits basically a mean position, a mean proper motion, and a parallax to determine the distance. Eventually, they will release all this time series data, and maybe before that, accelerations as well. But right now, the main observable is the stellar velocity and its error. And so the error right now for the brightest stars, sorry, not right now, but at the end of the Gaia mission, is predicted to be on the order of a few microarc seconds for the brightest stars and milliarc second per year for fainter ones. And here I've also plotted the intrinsic proper motion dispersion from the physical velocity dispersion in various targets. So you see that in the Magellanic Clouds you get on the order of 100 microarc second per year proper motion dispersion. Even cold targets in the Milky Way are not so suitable because they have quite a large velocity dispersion. And Andromeda would be the ideal target if Gaia could resolve a high density field of stars in Andromeda. Okay, so let me recap for a second. So the basic idea is that dark objects can weakly lens the proper motion and induce proper motion corrections on luminous objects. So then you can pick any of your favorite dark object and any of your favorite any of your favorite luminous source and use the observables that I just quickly outlined. Because we only have access to proper motions in the Gaia data set, I will talk about these velocity-based observables for subhalos in the Milky Way. And so I'll mostly talk about this velocity template analysis on the Magellanic Clouds. And then afterwards, about the proper motion power spectrum in the Gaia quasar data sample. But there's a program of analyses to do in the next several years. Okay, so let me tell you about the analysis we did now. So the question we wanted to, suppose you ask the question, is there a lens at some tentative lens position theta t with angular size beta t, so its radius over the line of sight distance, moving in some direction d hat. The test statistic that best answers this question is basically this matched filter, where so the test statistic tau is you take all the stellar proper motions behind that lens or around that lens and dot it into the shape of the signal and weight by the inverse variance of each star. Take the sum. And so for a truncated NFW profile, so the template for a lens moving to the right in the right ascension direction here is a dipole pattern. So the horizontal component is displayed here and the vertical component here. And note that so far outside the lens, so at the edge of this plot, it's basically a universal dipole pattern. So that this template would work to order 1 for any lens density profile, and you get sensitivity to the internal density profile at small distances here. Okay, so we're looking for this pattern here with this template. Okay, and so let's do some estimates of what the signal would look like. So the proper motion for a signal is just a template by construction times this quantity here, the lens mass and the lens velocity over the radius squared. So if you then compute the test statistic for a signal, assuming you've put the template in precisely the right spot with precisely the right size and direction, is this quantity here, 4 times, so the same prefactor times this normalization factor n squared. And yeah, so let's suppose the noise had 0, so the stellar motions in absence of lensing had no mean velocity, but just had some variance per star that could be different. So then the average template test statistic would be 0, but the noise, the variance of the test statistic would be n squared. So therefore,
So could you remind what exactly this mu's are?
So mu is the proper motion of a star, okay? And so mu I signal is the expectation of the lensing correction given a lens at the right location, right? And so by construction, I mean, when I say we do a matched filter, the template that we use in our test statistic is precisely matched to the, the mu is basically, the mu is basically this dimensionless template here. So it's the shape of the signal, and the signal is just this prefactor times the shape. Yeah, does that make sense?
You're not making any use of the three-dimensional information?
No, we're not making use of radial velocities. We are making use indirectly with parallax to cut out for foreground stars, etc.
Right, but I would imagine that since you're looking for a differential effect, you would do much better if you said, let's look at stars that I think are a kiloparsec away.
Yes.
And stars that are 2 kiloparsecs away.
Yes.
And look at the difference between their astrometric motions.
Yes, good. You could do that in principle, and that would be a telltale discriminant if you saw a tentative signal. However, the best stellar targets, we want the physical velocity dispersion of the stars to be small, meaning that they have to be quite far away, and the best targets for us are the Large Magellanic Clouds. And there we cannot tell if the star is 50 kiloparsec away or 51 kiloparsec away. The Gaia parallaxes are not yet good enough. Yes, yeah.
So you want to apply this towards the Magellanic
Yes,
Clouds,
yes.
as we think of this, not within our own galaxy.
Currently, no. If you want to do it in our own galaxy, you cannot do velocity templates. You would have to use acceleration templates because those are accelerations are small in the Milky Way, save for potentially lensing. And there, indeed, you can do what you suggested. You could modulate the template with 3D information with the parallax as well.
I'll discuss it later.
Yeah, thank you. Okay, good. So this is the value of the test statistic for a signal, and for the noise it's 0, but with some variance. So that means that if you put a lens in one particular spot and place the template in exactly the right spot, then your signal to noise ratio locally, without look elsewhere effect, etc., would be this. So this, again, this combination times this normalization factor n. If you plug in what the expectation value is typically for n, let me remind you, it was just the template squared with the inverse weights.
What about the orientation of the template? Do you try to maximize the signal or anything? Or
I will talk about that. So it turns out that they're orthogonal, so you only have to do the template in 2 directions, and then that's enough to reconstruct all the possible information. It's not immediately obvious.
No, I can see why it would, but I'm not seeing how that fits with the analysis.
So here for this exercise, let's say you wanted to, let's say you knew the lens position, size, and direction, and I'm just asking what's the best discriminant to detect whether the lens is there and only there or not at all, right? Of course, we don't know the lens position, so we have to test. We have to do a scan over all possible lens positions. We have to test this template everywhere in the Magellanic Clouds.
With all the rotations.
With only 2 rotations,
right.
And for a variety of sizes. Yes.
So you're summing that whole thing, or are you doing it locally?
I will show you precisely how we,
I guess I'm confused when you talk about a test statistic. Is it for a single orientation, or is
this is for a single location? I will tell you the right test statistic to answer the more global question. Yes, later. Yeah. Thank you. So for the local test statistic, it's this one. And you'll see that the local signal to noise ratio is dominated by the closest lens. So if the lens were closer, we get a bigger signal to noise ratio. So among the whole Magellanic Clouds, where the signal to noise ratio would be maximized would be from the lens that is closest to us. And that depends on the lens mass and the fractional abundance in this ratio. So that's typically the expected minimum line of sight distance for the closest lens. And the signal to noise ratio depends on the properties of your data sample just via this simple ratio. So that it's the square root of the typical stellar number density, angular number density of stars, divided by the typical error on the proper motions. So if you plug in this formula, this is what the signal-to-noise ratio looks like. So it scales like mass to the 2/3. It only has a very weak scaling with the abundance of subhalos, only the 1/3 power, a fractional abundance, and it scales like the inverse size of the lens. And then you want to maximize this quantity over the potential targets. And that's why we picked the Large Magellanic Clouds, because it has a very high stellar number density. There's a large number of stars, some of which have fairly good proper motion error, and it's a fairly big patch of sky. Okay, good. So that's what I just said before. So because they're far away, the Magellanic Clouds have low proper motion dispersion, and they have large stellar densities. So this is the sample we use, roughly a 10 by 10 degree patch on the LMC, and a little bit smaller for the SMC. We did some quality cuts on this sample, and we also removed dense foreground dense stellar clusters that are not part of the Magellanic Cloud. And we also cut out foreground stars with observable parallax. So all of the stars in the sample have no observable parallax, at least not at more than 2 sigma. And we also subtracted the large scale motion. So if you take the raw data from before and you plot the motion in the horizontal component or the motion in the vertical component, you see these, of course, big large scale patterns. It's also not centered at 0 because the Large Magellanic Clouds, both of them are moving, and this pattern here is from the rotation. But if you subtract this motion with some smooth, relatively large Gaussian kernel, you can get essentially a 0 proper motion, a proper motion field here that's basically just white noise. And of course, the noise is smallest here because we've been in the center, because we've been by pixels, so things average out in the middle. And we do this iterative procedure, so we also cut out 3 sigma outliers. So we don't, so to ensure that our test statistic is not dominated by mismeasured stars or high velocity foreground stars for which Gaia for some reason didn't detect a parallax. So as best as we could tell, these are the stars that are bound to the Large Magellanic Clouds and not in the foreground. So after that data cleaning procedure, this is what the actual data looks like in terms of proper motion dispersion as a function of magnitude. So the gray are the typical physical proper motion dispersions, about 100 microarc seconds per year. Green is what Gaia reports the uncertainty as on the proper motion. And blue is the effective standard deviation in each G magnitude bin. So you see that it roughly matches the sum of quadratures between the Gaia spread and the intrinsic spread in the proper motions. And in red, I plot the occurrence, so the number of stars in each bin. And so again, looking at our signal-to-noise ratio, it's maximized for the largest value of square root of the occurrence over the error, and that actually turns out to be on the red giant peak. So we're at the moment, and this is very important, at the moment we're still statistics limited. So as Gaia collects more data and has a longer time lever arm, our sensitivity will continue to improve, and very rapidly. I'll show you later. So basically, to the right of this pink line, we're still statistics limited. And so, yeah, what do we actually do? So we take this clean field of LMC motions, and also for the SMC, and then we compute our test statistic on every possible location. So we overlay our template, and we dot the proper motion of each of the stars, signified by these pixels here, and we compute our test statistic by dotting it into our shape for both motion components. And we do that for this angular size and this location, and going to the right. We also do it going up, and for every other lens angular size and every other location in a dense scanning grid. So here I show you the raw output of our test statistic. So you can compute the test statistic for the dipole going to the right here, or the dipole going up there. So that's tau alpha and tau delta. And so here I show you the histogram over all possible locations over this dense scanning grid in the LMC. And then the different colors are different lens sizes. So you see it's well approximated by at least out to several standard deviations by a Gaussian. And a lensing signal would occur in the tails.
So can I
Yes.
ask, so are you limited? You're not limited by Gaia measurement errors. You're limiting by intrinsic dispersion.
We are currently limited by Gaia measurement errors, right? Because most of our sensitivity actually comes from this region, so magnitude 16 to 19, and most of it is actually coming from magnitude 19. And at magnitude 19, it's dominated by the Gaia errors.
So for a single template for localized
Yes.
sources, Gaia measurement errors, do you know whether they're correlated between the stars which are close? Or the
Gaia does not report correlations between the stars.
But isn't it important for your analysis?
It is important. As at the moment, we don't have evidence of that effect. So there are large-scale correlations in the motions of even the quasars, which should not have any motion correlations. There are correlations on large angular scales in the Gaia data, as measured on the quasars, for example, but not on small scales. I mean, maybe lensing does, but we've investigated this, and it seems that to a large degree, there's very little correlation from star to star on small scales. That could change in the future as the measurement improves, but not yet.
What do you quantify as small scales there? 'Cause if you go back to your plot, you can see the correlation in the proper motions, even in your removed.
Here it should be consistent. There are some bands, so
Yeah.
where Gaia has scanned, there's larger noise. But my claim is that there's no correlated motions on a scale below 0.1 degrees in the Large Magellanic Clouds. But yes, the error varies, in these streaky bands. Yeah. Eventually, of course, that would be a problem because that could fake a signal. But at the moment, there's no evidence of that yet, and you can do estimates that we don't think it should show up anytime soon. Okay, so we compute the template in every location. We have our local test statistic distribution. This is what the magnitude looks like. It's the same as before, just compute the magnitude of both components in quadrature. This is the normalization factor. It's not so important. So okay, but the real question we want to answer, and Glenn has alluded to already, which is that we want to investigate this hypothesis, right? That some fraction of dark matter is in lenses of a certain mass and radius. We assume that they're distributed like the density field in the Milky Way, and we assume a Maxwell-Boltzmann distribution with dispersion sigma v of around 160 kilometers per second, and boosted by and we boost in our observer reference frame because of the solar system velocity through the Milky Way. And we want to investigate this hypothesis and whether it's right or not, or whether we can exclude it or not. So to do this, we created a bunch of mock data samples where we injected data-driven noise from the plot before, as well as signals according to the above hypothesis. And then we ran those mock data sets through the same data cleaning and data analysis pipeline as we did the real data. And so this is a picture here on the left. I show the actual data on some small patch of sky. And then on the right, I inserted a lens of 10 to the 8 solar masses that was consistent with being a point source. And you see there's a proper motion correction to these stars. By eye is hard to tell, but our test statistic evaluates here to 7 or 8, which is borderline detectable and larger than anything we saw in the data. So this lens would be detectable by our test statistic. And this is another plot to show you this. So this is actually not a proper motion field. This is this test statistic evaluated over many different locations on one small patch of the LMC. This is the data. So for a lens going to the right, a lens going up, there's no large, there's no evidence for a lens moving to the right or up in this small patch. But in the simulation, we've injected a lens again with the same parameters, 10 to the 8 solar masses and 1 parsec, moving at 10 to the minus 3 the speed of light to the right, and our test statistic picked it up perfectly here, and in the orthogonal component there's no signal. All right, but so to answer Glennis's question, and to you can construct the optimal global discriminant with this hypothesis versus the null hypothesis. And roughly what it is you take pretty much the largest tau, normalized tau value, so this tau over this normalization factor, the largest over all of the locations you've tested and over all lens sizes you've tested. And the expression looks a bit complicated, and this is to optimize our sensitivity, so you can take into account the fact, for example, that we're moving through the Milky Way with some velocity, so there's actually a preferred lens velocity direction. And you can also introduce nuisance parameters, or if you do the full likelihood, some locations are more likely than others, and in particular along the line of sight. Most of the volume is at large distances, so at small angular sizes of the lens. So this is the optimal test statistic. So we distinguish between the null hypothesis and our positive hypothesis if by computing this test statistic over each instance of our simulation. And if we find that in our simulations, more than 90% of the time, this R test statistic is bigger than the one computed for the data at some parameter space point, then that point is excluded. Okay. And so this is the limit we arrive at in the end. So at the moment, it's not yet a physically very interesting limit. We set a limit at about 5 times the dark matter density along the line of sight to the Large Magellanic Clouds. For a 1 parsec lens radius, and this is what it is for half a parsec radius, or basically point-like limits. The red curves are at 50% confidence levels, indicating that we could have seen something had the substructure fraction been large. But what I want to draw your attention to is that the proper motion error scales like the integration time to the -3/2, right? So there's one factor of 1 over root t from just doing more measurements, and another factor of 1 over t because you have a longer time lever arm, right? Yes.
So the lens mass range you're probing is 10 to the 7 to 10 to the 9?
At the moment, yes. Yeah. You can probe smaller lens masses with denser data samples, like Andromeda, for example, or in the future if Gaia can resolve more stars.
And this was assuming it was an NFW profile?
Yeah, truncated NFW profile. So we've taken NFW profile and we cut it off at the scale radius, or a few times the scale radius. Good. So, but the proper motion precision will improve like the -3/2 power. But looking at this formula here, because of the weak dependence on the abundance, the fact that we only got the 5 here now actually does not mean much, because it will increase, or the substructure fraction that we're sensitive to will decrease like a very high power with integration time. So even with DR3, which will come out at the end of this year, we will move down in physical parameter space. And by the end of Gaia mission, all of these curves should shift down by a factor of 1,000, or let's say by a factor of 100, but then we're also sensitive to more extended lenses like 10 parsec and larger. So in the future, these constraints will be very meaningful. Okay, I have 10 more minutes. I just want to give you a quick taste of what you can do with global signals of this effect. So the basic idea is that, so for a single lens, there's some real space distortion given by this formula. You don't have to remember it too much. But in Fourier space, so if you take the Fourier transform of this, this is what it looks like. And so there's some integral over the lens density profile that tells you how this Fourier amplitude depends on k. And there's some dependence on the direction and velocity of the halo. So what you can do is you can take a map of the whole proper motion density field of quasars and decompose it into vector spherical harmonics. And the lensing signal should show up in these coefficients. And in particular, we find that the lensing signal is only contained in this first coefficient, so in the poloidal vector spherical harmonics, not in the toroidal one. Basically because you can write this field as a angular gradient, so the second amplitude is 0 for the signal. There's also a directional asymmetry, so this power spectrum is greater for the high M modes, basically because there's some asymmetry in R velocity through the Milky Way. This is in galactic coordinates, by the way. And then we can also look at the shape of the power spectrum to disentangle noise from actual signal. So let me tell you what we want to do. So we take the proper motion power spectrum of quasars, and we want to we take these real space map, and we want to take a power spectrum of this. So here we've done a signal-only fiducial CDM injection. So this is what, if the stars were perfectly measured, and if the quasars were perfectly measured and had 0 intrinsic velocity, this is what the velocity field would look like. And likewise, the acceleration field for a CDM. And so we've done already some proof of principle analysis on the quasar. So there's about 500,000 quasars measured in DR2. This is one component of the proper motion, and this is the other. So right now they're measured at milliarc second level or so, so not quite good enough yet. And this is the magnitude and the error. So flipping between these two, you can see that there's, at least by eye, there's no indication that the motion is anything other than instrumental noise. And this is what the power spectrum looks like. So if you decompose it into vector spherical harmonics, what we want to do is compute the power spectrum of these poloidal modes where the signal should be located. And we can also, as a control channel, compute the toroidal power spectrum. And the signal should show up in the difference. So this graph should be colored in red at the high M modes for a signal. And we did some fancier thing where we weight the quasars with their inverse variance, which improves the sensitivity slightly. And we also introduced the spectral binning method, basically binning M and L modes that makes the analysis faster and makes it possible to go to much higher L. And so, yeah, and again, the signal should show up here, but we find no evidence yet, nor do we expect to find any. But over time, the signal-to-noise ratio will increase also quite rapidly and is sensitive to a different combination of lens population parameters. Okay, any questions about the local or the global analysis? Okay, I'll conclude with what you can do in the future. So to summarize, by the Gaia end of mission, so this is as a function of scale density of the halo and halo scale mass. We think that with Gaia, you can by the end of mission, this local template analysis test statistic will already dive into meaningful parameter space. So this is for a 20% substructure fraction. We can look for these quite extended halos already. This is with the velocity correlation power spectrum. And with angular accelerations in Gaia, we think we can do this red curve. If you do something more futuristic, like with a super Gaia, for example, there was a proposal a few years ago for Theia, which is an improved version of Gaia. We think you can drastically improve on this angular acceleration power spectrum. Or with SKA, or a similar astrometric survey of quasars, we think eventually you can look for CDM or for high density, low mass subhalos. And if you want to phrase it in terms of primordial power spectra, by the end of the Gaia mission, we think there's already some sensitivity, and in the future, we can see small increases in power for non-standard primordial power spectra. You can also look for very compact objects. So here I'm plotting the abundance on a log scale for very compact objects, for example, like primordial black holes, as a function of mass. And using this multi-blip signature, this transient signature, we think we can do at the end of the Gaia mission this triangular wedge here. And with the monoblip method, if we're not plagued by systematics, then we think we can look for very, very tiny fractions of black hole abundances. I'll skip this animation, but I think we can also look for planets in the solar system this way. So a planet in our solar system is basically doing the same as a dark matter lens, except it's moving much faster. Unfortunately, it's very hard to image because of paying Gauss's law twice in the reflected sunlight. But the lensing signal is not that small. So even an Earth mass planet, if the impact parameter is an AU, which is a large impact parameter, it produces a sizable lensing deflection. And even if it's 1,000 AU away, so at the edges of, or approaching the edge of the solar system, its motion is so large that the impact parameter changes by order 1 for 400 stars. So it would look more or less like this picture, at least in one instance of time. And again, you can do, instead of a matched filter for proper motion, you can do a matched filter for this full motion template. And we think the sensitivity for such a template analysis would only scale like 1 over the line of sight distance to the lens, much better than direct imaging searches. So at the end of the Gaia mission, we think we can look for planets below this dark orange curve. So for example, we can see a Neptune-like planet down to up to 1,000 AU or so. And the tentative indications of planet 9 are in this region. So we could exclude that possibility if it's in a favorable patch of the sky. Okay, I'm about to finish up. So I think already with Gaia astrometry, you can do amazing things, and there's lots of hope for optimism in the future with surveys like Theia and WFIRST. So one of the things that we realized was that you don't necessarily need good global astrometry like that Gaia provides, but what you actually need is great relative astrometry. So even imagers like Hubble images or those produced by WFIRST, even better because they're larger field of view, we think will be quite sensitive for these astrometric weak lensing searches. So as the precision of these surveys approaches the microarcsecond level and very high statistics, we think this is a great way to look for completely dark objects in our Milky Way. And with time, we think this will be one of the most sensitive techniques to measure the motions of dark objects in the galactic halo. Thank you.